Hi, thank you very much. So welcome to a hacker's guide to analog design in a digital world. I'll jump right in. So thank you for the introduction. As you had said, my name is Nanik Adnani. I'm an analog mixed signal design engineer, maker, hacker, proud black cat owner. Her name's Ada. The last line's true. You can ask me about that later. All right, so the first thing I wanted to do today was just quickly define analog electronics. I get a lot of questions at this conference. When I say I'm an analog designer, I get a lot of, how do you make money with vacuum tubes in 2024? The answer is, I don't. So analog electronics is the design of electronics that create or manipulate continuously variable signals. So that's the definition I came up with. You might ask, what's a continuously variable signal? Well, pretty much all signals, even the digital ones, which is what we're going to get into. All right. So in the world of analog IC design specifically, there's two things you can do. You can move data and you can collect data. So to start, I'm going to talk a little bit about the collection of data. Well, actually, I'm not going to talk about the collection of data. There's another talk you need to go see to learn about this. Azita Amami is going to be presenting on the intelligent brain interfaces. If you want to learn about data collection with analog design and sensing, go there. I'm going to talk about the movement of data. So to get started with this, we've all probably tried to send a digital signal at some point. I think most of us have succeeded at that. And this is probably what we think it looks like. We've got this really nice square wave here traveling along the line between the integrated circuits. I hear some laughing, so you probably know what's coming next. This doesn't exist. This is, oh, it's doing something. Hold on. Yes, there we go. Yes, that's what it actually looks like. So this is the real world. As you can see, our nice square wave is now like barely a sine wave. And so we have to find a way to transmit this data and then also recover it and take this sine wave and turn it into something we can actually read. I can't get a 1 and a 0 from this. I'm guessing you can't either. So the question here is what is happening in the real world that takes our square wave and turns it into this little squiggle here. There's tons of things like substrate losses and conductors, and as you increase frequency, you'll have to impedance match and do all that stuff. But I think the simplest place to start is I'll just talk about capacitance. So here we have a logic gate that you'll find on an integrated circuit, and then next to it I've got the pin on the integrated circuit. Can anyone see the logic gate? Someone, maybe? If you can, you should get your eyes checked because there's nothing there. Yeah, so you can imagine we've got this logic gate that's so small I didn't even bother putting it in the slide. Next to this pin here, which we're used to thinking is very tiny. I'm sure this pin does not feel huge when you're trying to solder a BGA. But relative to that logic gate, this is massive. So if I say something like this pin has a capacitance of like a couple hundred femtofarad, you can imagine trying to drive current through that logic gate to charge this pad. It's going to blow up. It's going to die. We're going to have to do some analog design to get us there. So I'm going to introduce this concept. What is a PHY? Has anyone heard of a PHY? Oh, okay. So I'll give a brief description. One more hand at the back. Nice. All right. So a PHY is short for a physical interface. So this is like basically an analog interface that will go between the logic you have on the chip and allow it to communicate off chip. So this will usually consist of some larger devices, so you can't take like a standard logic gate and directly send it off chip. So you'll have larger devices, and yeah, that's pretty much it. It's pretty simple. So let's take a look at some PHYs. First off, all of the digital protocols that you're probably familiar with actually are based and require analog circuits. So we've got CAN there. Thank you, Randy, for the talk on CAN. That's an interesting PHY case. Like, we can talk about why it's split up between multiple chips most often and why the NXP chip is $20. Yeah. All right. So let's look at some. So this is the Apple M3 lineup. And we can actually really clearly, I like this because in their die shot, you can really clearly see the PHYs that they've got here. And I'm going to focus in specifically on the LPDDR5 PHYs. This is low-power DDR5 that are on the edge of the M3 Max chip here. Oh, I can point. Okay. So they're surrounded in this yellow square here. You can see there's actually 4 PHYs there. They're kind of one. Okay, I'm guessing there's 4 PHYs there. Apple won't tell me. But you can see them lined up there and reflected, and then there's like 2 here kind of stacked next to each other, which is really difficult to do. I tried. So Anyway, yeah, you can take some time and look at the rest of the M3 chips and try and find them. It's like a scavenger hunt. Maybe a chip that we like a little more at a conference like this is the RP1. So is anyone familiar with the RP1? A little bit? Okay, so in the Raspberry Pi 5, the Raspberry Pi team actually came up with a piece of custom silicon to manage all the I.O. So the GPIO header on the Raspberry Pi, you can imagine if our logic gates are that small and we can't charge a pin, good luck charging a GPIO pad. So they've developed this chip here to go between the processor and the GPIO header, and it's a chip full of different analog designs, full of PHYs, I think mostly from Synopsys and a couple other vendors. So they've bought these analog designs and put them all together, and this is what makes the Raspberry Pi a Raspberry Pi, is this kind of neat piece of analog design. We can go through and play a guessing game of what those are, but we'll probably won't be right about it. One I am certain about, though, is on the RP2040, you can actually see the USB PHY. I really like this one because USB is like a differential signaling system, and it's really easy to see that it's just one design and then reflected over. I find that kind of cool. The other thing you'll notice, too, is like we're just looking at top layers here. So this is just the top metal layer. And so you can't really see anything that's going on in here. There's a ton going on in the middle here. But the interesting thing about PHYs is they're usually drawn by a separate team, by the analog team, and the metal layers are optimized in order to get power down to the transistors as quickly and efficiently as possible, and in specific areas. So that's why the metal layers are different, and that's why they're really easy to identify. All right, so we've talked about what a PHY is. We've looked at some pictures. Let's build one. So I've got a bit of an example here. I wanted to, I'll design an LPDDR5 PHY, but, JEDEC says that's confidential. So here's a walker. Probably weren't expecting. This is my favorite project. My grandmother this summer needed a walker to help with some mobility issues she's been having, and she didn't want just any walker, so I added some features to it. There's RGB lighting. There's there's a car horn, and that water cup there is a water gun in disguise, so she can spray her friends when they're least expecting it. But today what we're going to talk about is the car horn. So the car horn is an interesting case. It's communication. We've got a digital signal coming from our chip, and we need to find a way to communicate that to the neighbors all the way up and down the street. So we're going to build a PHY here. You can see kind of the problem distilled down into the simplest form is our microcontroller can likely only output about 40 milliamps, and the horn needs 8 amps. So that's not going to work. We're going to kill our poor microcontroller. So let's design a PHY. But before we design a PHY, with analog design, it's important to remember you always have to check to see if someone else has solved it, because analog design is expensive and takes a long time. I couldn't find a horn PHY, so we'll move on. All right, so here's the design I came up with. It's really simple. That's the point. I'm driving the horn with a PNP transistor. I used a PNP transistor because a fellow at our local surplus store convinced me to buy a lot of PNP power transistors. And I'm driving the load here. The horn is being simulated with this 1 ohm resistor. It's in the box. This part works. We can use a power transistor and we can drive the load, but then how do we get the microcontroller to drive it? We need some way to tie the base of this device to 12 volts and then pull it to ground. An Arduino can't do that, so I just put an N-type device in there. So it should be relatively simple, and I hope everyone can kind of see that it's simple, and you're probably sitting there thinking to myself, I didn't realize I'd made a PHY before. But yeah, so we can test this out. I only have the simulation results. We got about 12 amps through the simulation. That's just because we've got 12 volts going through a 1 amp resistor. It did work in the real world, but I asked my grandmother for a picture, and that didn't go particularly well. So, yeah. So again, here we've got this really simple PHY, and I hope that makes sense as to what a PHY is. We've got something that can have data within itself. We need it to get that data into the outside world, but that requires driving something much larger, driving a lot of current through something. And so we've done that. Okay, so this is cool. We've learned that analog designers don't just work with vacuum tubes and play a critical role in what we do. But what does that mean for hackers? Because, realistically, I probably should have used a relay here. That's what cars do. So what else can you do with analog design if you're going to learn some of it? Well, I've got some projects here to go through. So first I want to talk about this cassette interface. So this is a blogger I found, Zach Nelson, figured out how to store data on a cassette using an Arduino. And it's a really cool project, and I love it because it's a super simple analog circuit. There's not even discrete transistors here. These are op-amps. So if you've taken like a first-year electrical engineering course or watched like 7 YouTube videos about how to do this, you can do this and you can understand it, and it's not that difficult. Yeah, so there's a PHY in the wild, in like the hacker wild. Okay. This is something I did. So if you're sitting and thinking, like, why would I learn analog design? I'm never going to be able to tape out. Well, you actually can. So I'll talk about it a bit later, how I taped it out. But this is a guitar pedal circuit I was able to tape out on an open source tech node. We've yet to see if it works. Matt somewhere, he's got the chips. He'll send them to me at some point. Guitar pedals are really cool because all the circuits are the same. A receiver on a very basic receiver in a PHY is pretty much a distortion pedal. It's the way it takes like a sine wave and blows it into a square wave is interesting. All right. I really love this project. This is by Kelly Heaton. She's got a whole series of different circuits, all kind of titled under electronic naturalism. And she's using these analog circuits as a way to kind of recreate and understand nature. When you're working with an analog signal, this is separate from the PHY idea, but her idea is that you become more attached and understand nature better. And I've tried to make some birds, which I guess is what we're talking about here. If you've seen me anywhere, I've made a whole bunch of analog SAOs. I've still got some left, so come talk to me at some point. This bird here is based off of Kelly Heaton's work and involves a couple oscillators. You can see the bird waveform on my oscilloscope here. And then also the flashing arrow. It's very bright. The downside to analog design is if I wanted to change how bright it was, I'd have to desolder and resolder 60 resistors. So it's not perfect. Yeah. All right. And this is the last one I want to talk about, this Fartbox project by Sam Battle, who goes by Look Mum No Computers on the internet. And I mean, it's really hard to talk about analog design without talking about music, which is something I'm kind of doing here. But I figure if you can make a synthesizer that farts, you can make any other circuit you want and any sound you want. So hopefully that convinces you. All right, so we've talked a bit about what you can do in industry with analog design. We've talked a bit about what you can do as a hacker with analog design. But how can you learn? So I chose the traditional method. I'm in school. It's a lot of work, but you don't have to go to school to learn analog design. And actually, a lot of these people didn't go to school to learn analog design. So it's entirely possible. But I will say one thing that's very beneficial are books. A lot of the information on the internet is not entirely true because it gets filtered through a bunch of different people. So the article you're reading is probably the third person to try building a circuit that the first person drew in the early 2000s, and the capacitor values will be all screwed up or something. And so start at the source. So I'm going to make a couple very quick recommendations. Design of Analog CMOS Integrated Circuits by Behzad Razavi. Start here. This is an excellent place to start. Then we can go on to, this one is a staple in Canada, and I think a lot of the world too. There's a slide where it's all summarized. Yeah. So this one's good if you prefer to understand things analytically. I'm not very good at math, so it doesn't work for me, but some of you are. So The Art of Electronics, you've all heard of likely. It's phenomenal if you're trying to get a board level design to work. These two focus on integrated circuits, so trying to get something on a board is a little bit different. This book is fantastic for that. Now, if you want to tape out, this is an excellent book, CMOS Circuit Design, Layout, and Simulation by Baker. Many analog designers have told me that this is how they survived their first tape out. So strongly recommend. And then this last one, Analog Integrated Circuit Design by Tony Chan Carasoni, David Johns, and Kenneth Martin, is great for some more advanced circuit theory concepts. I'm struggling through this one in school right now. Okay, so here's kind of the summary. While I'm on the summary slide so you can take pictures, I want to say a lot of people I've suggested, I had to do some training a couple months ago, and a lot of people said, oh, well, I sat and read Sedra and Smith cover to cover, and I don't understand analog circuits, so all hope's lost, I'm not going to learn. Please don't do that. Read like the first 3 chapters, try and build something, go back to it, use them as a reference. I had one professor tell me that all you really need is the first 4 or 5 chapters of Design of Analog CMOS Integrated Circuits by Behzad Razavi, And then you can start building things. So that's where we'll get to how to start building things in a minute. So some online resources. There are some excellent online resources. I really love this YouTube channel. Moritz Klein creates these music projects. And I think they're excellent because he doesn't dive too much into the details of how to bias things, but he walks you through the thought process. So there's some circuits in an LPDDR5 PHY somewhere inspired by some of his videos. Karsten Wolf is the IC scientist at Nordic Semi and also a professor in Norway. And his channel is phenomenal if you want to start taking the step from board level stuff into integrated circuits and you're interested in a career in analog design. He does some excellent overviews of what it means to be an analog designer and the kinds of things they'll be working on. I had to get a job to figure this stuff out. You can just watch it here. And then the last recommendation I'd say is Ali Hajimiri's YouTube channel, where he's posted tons of videos he's taught at Caltech just down the street. So if you want to see a university-level analog design course for free on YouTube, and a very well-taught one at that, this is the place to go. All right, so all these resources are great, but as I said, if you read the whole book cover to cover, you still won't be able to do any analog design. I wouldn't be able to. So what you have to do is practice. So I'll introduce you to the best investment in my analog learning adventure. This was $2 on AliExpress. Most of them are burnt. That's okay, that was the point. But you can build pretty much anything you see in any of those textbooks with this. Some people will tell you you can't. For anyone who has done any analog design, I was told I couldn't build a discrete Gilbert cell mixer. Turns out you can if you're stubborn enough. So definitely start with something like this and build stuff. Simulations can save you a lot of time. I've put these two up here because they're free, and if you've ever tried to pay for industry simulation tools, free is a lot cheaper than tens of thousands of dollars. So LT-Spice I love for discrete simulation. It's great. Lots of the models are built in. NG-Spice is great if you want to tape out. That's kind of how I use them. Mix and match however you like. And then Matt's somewhere, but there he is. You can tape out an analog design now for 400 Canadian dollars. It's awesome. To put that into perspective, it sounds like a lot of money. An analog design course at the University of Toronto, if you're a Canadian citizen, is 1,200 Canadian dollars. And you can learn a lot more by taping it out yourself. If you do them both together, it's cool too, but yeah. All right, so, and now just the last little bit. I want to make sure I definitely reiterate that you can learn analog design. This is not some I'm not a wizard with a hat. This is not impossible. It's very practical. Unfortunately, some people have tried to make it more difficult. This is a comment I stumbled across on the open source Silicon Slack while I was trying to learn. So if you're ever sitting there frustrated at a circuit, why won't someone just tell me the answer? It's because they've chosen not to. So keep going. You'll be fine. And if you still don't believe me, I will now reveal I am actually still a student, and actually an undergrad student at that. So if I can figure all this out, you can too. Okay. Oh yeah, I had a slide to say that. Okay. That's all for me. If you have any questions, please let me know. Thank you. Any questions? Yeah. This one? This one? This one. Okay, yes.
I got the latest version and then found out immediately afterwards that the people that wrote it all at Winfield went a different approach with the latest version.
Okay.
It's less introductory and more high level.
Okay.
And a couple of people feel that the third version is the one that happens.
Okay, so get the third improved edition. That's because my copy was actually my father's copy, so it's like the first edition. That is awesome. Good. Yeah.
I mean, but also that's what I read on the internet. Validate for yourself.
Yeah. All right. Any other questions? Yeah. I will put them. We'll get into it on this website, nanik.ca. It's very easy. If you have an uncommon name like mine, you can just... Yeah. Yeah, I'll put those there in like the next hour. You can find them there. Awesome. Thank you.